Welcome everyone. Thank you for attending the high-speed data transfer at the University of Otago session. My name is Carmel Brown. I'm from Queensland University of Technology, and I have the pleasure of introducing today Douglas Hare from RIANZ. He's the Chief Engagement Manager. He works alongside members to help them get best value out of their RIANZ connection and to enable them to achieve their strategic vision. Also, we have Dave Maclaurin from the Uni of Otago. Dave has over 20 years enterprise IT experience, including roles in system analysis, design, development, database administration, and IT management and governance. He and his team is also responsible for architecture, procurement, and implementation of ITS compute storage solutions. Oops, I'm going over the page. And also some of Dave's team works with the national NESIS service delivery teams. So can you please join me in welcoming David and Douglas?
Hey Dave. All right for Dave.
I'm going to start, and then I'll hand over to Douglas, and then it'll come back to me again. So it's a bit of a joint presentation. So this presentation is about the development of a high-speed data transfer service at the University of Otago. A wee bit of background on us. We've got around about 18,000 students and around about 4,000 staff. We are a NESI investor, so that NESI is the New Zealand e-science infrastructure, supercomputers basically, and we're a RIANZ partner. We've got large research data storage clusters in place already. Now this slide is actually now out of date because it says 2.4 petabytes mirrored. It's now around about 4. And we're transitioning to a brand new university network, which is ongoing. So why did we decide that we needed a high-speed data transfer service? Well, we had NESI, and the main NESI facility that we use is in Auckland, and we're down in Dunedin, which is a wee way away. And some of the workloads were changing, so we're beginning to see larger and larger data sets that people wanted to shift. This was brought to a head in 2016. We had 2 projects come along, one a large genomics project and the second one an MRI project, both of which were either creating a lot of tiny files or a lot of very big files, and either way we had no way of getting that data on and off campus efficiently. Since we had our storage clusters in place, we really wanted to be able to take advantage of them for our research community. So, you know, to begin with, they could use those on campus. They couldn't really access them from off campus. They certainly couldn't transfer data around the place. And we had a lot of people using the external hard drives wherever they could get them. They used couriers, they put people on planes, they shifted data whatever way they could, and it was quite hard and painful. We still have a few people doing that, but we've got a lot less doing that. So these were all sort of the reasons why we decided we needed to do something. As part of our new network, we put in a brand new commodity network edge, so designed to handle thousands of user connections concurrently, but it's not designed for large research data flows. They're really quite different. So instead of a lot of 300 megabit a second connections, we wanted to do a few very large multi-gigabit connections and have them work. We made a few attempts valiantly. We tried a few things, looked at our infrastructure and decided that we'd call RIANZ. And so at this point I'll hand over to Douglas and he'll take you through the next few slides.
So RIANZ, for the Australians in the organisation or in the audience, is the New Zealand equivalent of ARNet. So we run a 20 gig network from the bottom of the South Island up through to the north of the North Island. Our connection point in the bottom of the South Island is the world's southernmost permanently connected research and education location. So the Chileans are currently trying to steal that from us. There's a few geographic pedants who say, well, what about connectivity in Antarctica? And it's true that the National Science Foundation does have connectivity into the South Pole, but that's done via satellite. So we like to say that because we've got a fibre connection into Invercargill, that's why it's permanently connected. So we've got a 20 gig connection, like I say, and Otago is our largest member in the South Island, and of course, being as how they're at the bottom of the South Island, they have to get their data up through what is a long, thin and mountainous country. The Science DMZ architecture that we have put into Otago was developed in the States, and it was developed to try and get around the fact that you've got scientists who are wanting to move often many terabytes of data, but you have security people often within institutions that are running, say, 1 or 10 gig firewall systems, and they get very nervous about people trying to send lots of data when the researcher comes along and says, can I bypass your system? So the Science DMZ was designed to be like a bypass around town. I can send a lot of data from point A to point B, but I don't need to go through the firewall at the edge of my network. I can transfer it around the side by having like a trusted connection. So when Dave's team contacted us, it was a great opportunity to be able to take this idea from the US that wasn't really being used in New Zealand and to sort of do it as a bit of a start to finish approach. Are you pressing the buzzer, or am I?
Sure.
All right then.
How's it?
Very good. So there were a couple of universities in New Zealand that had done in-house science DMZ types of approaches. The good news with Otago was they came to us at the start, and so we were able to work with them from the start on the design, in the middle on the implementation, and then at the end, once it was all done and dusted, we were able to run a sort of a post-implementation process. So, you know, when you dream about having something that works from start to finish, often it doesn't always happen that way, but in this particular case it did, so we were pretty pleased how it unfolded. As Dave has alluded to, there were already some ideas from the Otago engineers about what were the issues that were causing hold-up, which is always a good point. So we think we know what was wrong, we're not entirely sure, so we could sit down between us and come up with a good solution. The upshot of all that was that we implemented the Science DMZ over a period of, what was the actual end time?
Well, the Science DMZ itself, I suppose, 3 or 4 months.
Yeah. So over a 3 or 4 month period, it's been up and running now for the best part of a year or so, and so we have been able to do a lot of post-testing. So there is a testing box perf sonar that we can put into these networks. It's a global network of testing devices. I think there's about 1,900 of these boxes around the world that enable research networks to test connections. We are currently deploying those around the country. Otago was the first one that we put in place, and that gives us a very good sort of almost an academic view of the data transfer rates. So that's probably where we got to, was just the implementation at the end. So probably back to you as to how we actually did it.
So along the way, we had a few challenges, needless to say. So quite apart from putting the Science DMZ in, we actually had to work out how to get data off our storage and up the country and then back down again. So one of our destinations was in Auckland, the Nessie Pan cluster. The other one was in the US. And at points along the way, we also had to bring data across from the US, so about 150 terabytes, I think, we brought over in the end. But prior to that, we basically had to work out how do we get sufficient data going off our storage or onto our storage every second without pausing, without stalls, without crashes, so that we could scale. We decided we needed large network pipes, and as Douglas said, we're now lucky enough to have the 20 gigabit link down our way, which we haven't actually stretched yet. So prior to that, we limited ourselves to about 5 or 6 gigabits a second. To get data into our pipe, say we were reading off our own disk and then transferring it outward, we had a fortunate coincidence where the clusters that we use for our high capacity storage are multi-node, so there's about 18 nodes, I think, aside. We actually just ended up allocating a bunch of nodes, each with fiber connections to our data transfer service, so we could just scale out the storage quite happily. I think if we'd been running monolithic storage with just a few connectors coming out of it, we'd have struck a few limits there. So we were quite lucky in that way. Even assuming we could get the data on or off disk, how did we actually get it onto the network connection and keep going? So we used the New Zealand eScience infrastructure reference design in the end, and they use Globus technology behind the scenes. So we researched that, we found out all about it, we worked with them on it, we liaised with RIANZ a lot, we did a lot of testing, The other thing that we found out was don't run the network connections at 100%. Never a good solution. always come back a wee bit. But quite apart from the technical challenges we faced, which we knew we would solve sooner or later, what we really wanted to do was to make this part of our researchers' natural workflow. So instead of reaching for the courier's phone number or their Dick Smith external drive or whatever it was that they were using, we wanted them to actually think of this as a service that was available regardless of where they were. So we have the service now in Dunedin, we have campuses in Christchurch and Wellington, and it's also running at those locations as well. We wanted to make sure that it was easy to use, so easy to sign up for, and that we asked sufficient information when people did sign up so that we knew that they'd thought about what they were doing. So we asked things like, do you know of any reason why you can't transfer the data to the UK? What sort of data is it? How long do you need that connection active for? And when do you want us to review the connection? So what we're trying not to do is just open connections through a high-speed service and leave them open. So we open them, we hand over to the researchers, they can schedule those transfers whenever they like through a fairly simple web interface. When they're finished, or at the review date, we'll revisit it, and if they don't need it, we'll turn it off again. Our biggest client in terms of data volume was the Genomics project, and they have been running, they wrote a whole pile of scripts, basically, that tied in with the NESI supercomputer in Auckland, and they scripted the transfers off the storage here, or first of all, sorry, over from the States to our data centres here, then up to Auckland, then back down again. So the whole time they're kind of polling for activity, looking for a job to finish, and once it's finished, they're pulling the data back down. So the whole thing was done using code, fully automated, running 24 hours a day. And that's the kind of level that I was really hoping we'd get to. I didn't want people to have to sit there and do things manually. For this to be useful, you need to be able to run it from whichever research workstation you're on and know that it's going to go. We wanted to make sure that it was going to be highly available and that we did test it every month, and if there was anything wrong with it, we would say and turn it into a really good service that people could rely on. And part of that, in the next slide, we put up a whole pile of material on the web announcing it. On the right-hand side of that slide, you can see some FAQs there. We emphasised the partnership between RIANZ and ourselves and NESI, because that was kind of crucial to this whole thing. And we provided as much information as we could so that people would know, what does this do, what doesn't it do, who do I contact, and all the rest of it. And then we basically went out. So we've spent quite a lot of time going around departments, doing presentations to focus groups, like brain research, MRI groups, that kind of thing, just to make sure they knew the service was there and what you could use it for. The service went live around April 2016, and the value proposition was basically that if you used our central storage, so we have around about 160, 170 departments, and we've got over 120 research teams now using central storage, which is sitting inside our data centres, right next to our network edge, right next to the transfer servers. So we wanted anyone who used our central storage to be able to take advantage of this. So that's basically how we promoted it. And what you find is you don't have hundreds of people coming to the door, but the ones that come to the door absolutely need to come to the door because they've got no other way of doing it. And we really wanted to be able to lift what people could consider in terms of research. So instead of going, well, we just can't even consider that research because we never get the data up and back. We could never do that in a timely fashion. We wanted to change that and remove distance. So they didn't really need to think about that. They could just get on with what they were trying to do. This is a bit of a graphic that should give you an idea of why we decided to do something. On the left-hand side is our first attempts at getting data on and off campus, science data. We managed about 40 megabits a second with a tailwind and a sail up. We discovered that a student over a short distance with running shoes and an external hard drive could get data off something and onto something else quicker than we could, which wasn't a good situation. Some parts of the campus were better than that, some were, so it just wasn't consistent. So this was our legacy network, our old network. As you go across to the right-hand side, you can basically see around about 300 megabits a second, we were putting our data out through our packet shapers. And at 360 megabits, the packet shapers chop it, leap in and go, no, I think this flow is getting too big. So then we decided we'd go around the side of that. We started implementing the new NESI reference design. And of course, we'd been working with REANS now for a little while. So we understood the science DMZ, and we actually made some quite major changes to our network edge to do this. Using a single node, we got to around about 1.8, 2 gigabits a second for a single server. We then decided that to really start pushing the boundaries, we needed more servers doing the transfers. So we now have 2 chassis of blades, around about 10 transfer servers running 5 each side, with spare in an HA configuration. The overhead of virtualization is about 6%. So you just take that into account, it's not too bad really. The right-handmost bars there, where we're getting up to about 5 gigabits a second, we didn't actually manage to do those in New Zealand. The only way we could hit that speed was there are some public sites, really good sites for testing Globus transfers. So ESNet in the States has got a great website, a lot of information, and public endpoints that you can download from. And CERN also make endpoints available for public use, where you can just try getting data down. So those high speeds we're actually pulling from overseas. We found that if we were pushing to destinations within New Zealand, typically the other end wasn't fast enough to receive the data. So it would just pull us back. That's since improved, but that was during our initial testing phase. This is a slightly horrible logical diagram of what we did. But if the most salient point is if you go to the very top there, you'll see the REANS network edge. And the difference between that and what we used to have, we just had a single conduit coming in. We now have 2. So if you take that central path going straight down, you head into our Science DMZ. If you go out to the right-hand side, that's the commodity connection. So that's going through the packet shapers, traffic inspection, firewalls, all the rest of it that you would have to protect users. So the Science DMZ, we went to a lot of trouble to eliminate single points of failure. We've got a large virtualization environment driving the transfers. We have proxy nodes to securely decouple our storage from the data transfer nodes. This is what it looks like when the genomics project was running till around about March, I think they were going. Around about 4 or 5 gigabits a second. We'd never really done more than about 1.5 out of the university at any point for any reason prior to that. And that just gives you an idea of what's happened so far. We're up around about 700 terabytes that we've transferred so far since it went live, and around about 50 million files. So the left-hand one, the terabytes, is genomics. The right-hand one is MRI, typically. And this is NESI's view across New Zealand of the data transfer nodes, which sort of coincides with us going live, and then other sites got in on it and started doing things. So quite a nice uptake so far. We have some case studies if you want to do more reading about this. So if you just look for the keywords there, or hopefully I think these slides are going to be made available to you anyway. So there's a good one that we did together with REANS and 2 for NESI as well. And just a thank you statement to a lot of people who've helped us out along the way. So REANZ have been unfailing in their support for us, which is really good because we'd have floundered in a bit of a mess otherwise. Nessie we've been working with a long time, and it was a good chance for us to work closely with them as well. And we couldn't have done this without ESNet and CERN having their nodes available. So thank you very much.